We want to find the flux of the vector field across the part of the plane given by z equals 3 plus 4x plus y above the rectangular region where x is on the closed interval from 0 to 5 and y is on the closed interval from 0 to 4 with an upwards orientation. If the vector field F represents a velocity field of a fluid flow, then the flux integral represents the fluid flow across the surface S. So if S is the oriented surface given by z equals g of x comma y, and R is the region in the xy plane, for an upward orientation, here's the formula we use for the flux integral. We'll notice how these first two double integrals we're integrating over the surface S, and this last double integral, which we'll use to evaluate the flux integral, we're integrating over the region R in the xy plane. So before we set this up though, let's look at this graphically. The vector field F is graphed in gray. The surface S is the part of the blue plane bounded by these four yellow planes, so this is the surface of integration. If we look down on the xy plane, the region R in the xy plane is this rectangular region here. So the value of the surface integral will give us the volume of flow across the surface S per unit of time. So going back to our work, because the surface S is given by z equals 3 plus 4x plus y, we know z equals g of x comma y equals 3 plus 4x plus y. So for our next step, let's go ahead and find these partial derivatives. So the partial of g with respect to x is equal to the derivative of 3 plus 4x plus y with respect to x, which would be 4, and the partial derivative of g with respect to y would be the derivative of 3 plus 4x plus y with respect to y, which would be 1. So again, the flux integral is normally given in one of these first two forms, where we have the double integral over the surface S of f dot differential S, which equals a double integral over the surface S of f dot n differential S, where notice this differential S represents a small change in vector area, and this differential S represents a small change in surface area. So these double integrals over the surface S are equal to the double integral over the region R of the vector field F, which has an x component of y. And now for the y component, which is negative z, we're going to substitute the quantity 3 plus 4x plus y for z. So we'll have the opposite of 3 plus 4x plus y, and the z component is x, dotted with the vector field where the x component is the opposite of the partial of g with respect to x, which would be negative 4. The y component is the opposite of partial of g with respect to y, which would be negative 1. And the z component is 1, differential a. For differential a, because this is the region R, the order of integration really doesn't matter. Let's substitute dx dy for differential a. So we have the double integral of the dot product. Let's write this y component as negative 3 minus 4x minus y. And again, differential a is equal to dx dy. Limits of integration for x are from 0 to 5, also given here. Limits of integration for y are from 0 to 4, also given here. Let's go ahead and evaluate this on the next slide. So now we'll find the dot product. So we'll have y times negative 4, that's negative 4y. And then we have the quantity negative 3 minus 4x minus y times negative 1. So we'll have plus 3 plus 4x plus y plus x times 1, so plus x. Let's go ahead and combine like terms. So we have negative 3y plus 5x plus 3. And now we integrate with respect to x. So we'll have negative 3y times x, or negative 3xy, plus 5 times x squared divided by 2, or plus 5 halves x squared, plus 3x. for big F of b minus big F of a, when x is 5, we have negative 3 times 5 times y plus 5 halves times 5 squared plus 3 times 5. And when x is 0, all terms will be 0. So we have negative 15y, and then 5 halves times 25, that's equal to 125 halves, plus 15 is equal to 155 halves. And now we integrate with respect to y. So the antiderivative is going to be negative 15 times y squared divided by 2, or negative 15 halves y squared, plus 155 divided by 2y. Performing our substitution, we have negative 15 halves times 4 squared plus 155 divided by 2 times 4. And then when y is 0, both terms are 0. So simplifying here, negative 15 halves times 16 is equal to negative 120 plus 155 divided by 2 times 4 is equal to 310, which equals positive 190. So this is the value of the flux integral, which remember does represent a flow across the surface S. I hope you found this helpful.